So, good evening. So, let's start with the next topic, infinite impulse response filters. Okay. So, if you remember correctly, in our last classes, in some of the last classes, we have been discussing about the FIR filter, and we have seen that the transfer function of the FIR filters are something like this, wherein there were no denominators. We were only having the numerators. Okay. So when we talk about the IR filters, so in the IR filters, what we have two types of polynomials. So first one is the numerator and the second one is the denominator. So numerator would be something like this and denominator it would be something like this. And if you try to solve this, say for example, if we go for the multiplication in the crosswise multiplication, and then if we want to go for the expansion, and thereafter if we try to isolate the yz, so we get the equation yz equals to this equation. Okay, xz plus b of z inverse xz minus a of z inverse yz. Okay, and then if you try to perform the inverse z transform to get into the time domain, then we get yn equals to xn plus b of x of n minus 1 minus a of y of n minus 1. Okay, so if you see the output of the IF filters, it is not only dependent on the present and the past inputs but also on the past outputs. Okay, so due to this reason, what happens is that this filter it is a recursive filter. Okay, because if you are taking output from the previous instances, so the what you call the inputs or the outputs what you will be getting, it will never be zero. It may be tending to zero, but it will never be zero. Okay, and hence it is regarded as the recursive filter. On the other hand, in the FIR filters, what we are having that the filter was only dependent on the present and the past inputs. So inputs you can make it zero. Okay, but in this case, even if you make the input zero, you will be getting some outputs. Okay, and if you are getting some outputs, so it cannot be zero altogether. So at time tending to infinity, our output would be tending to zero. Okay, for a stable filter, obviously. Okay, so next, let us take one example wherein we are having a transfer function h of z, it is equals to 1 by 1 minus a z inverse. Okay, now if you multiply both the numerator and denominator with z inverse, what you get, we get the equation hz equals to z divided by z minus a, where we can see that 0 will be at 0, that means at the origin, and we'll be having a pole at z equals to a. Okay, now let us take three cases. The first case is a equals to 0.5, a equals to 1, and a equals to 1.5. So when a is equal to 0.5, it is within the unit circle. When a is equal to 1, it is on the unit circle. And when a is equal to 1.5, it is outside the unit circle. So we all know that in the first case, it would be a stable filter. In the second case, it would be a marginally stable filter. And in the third case, it will be an unstable filter. So, if you see, we have plotted this pole zero plot. If you see over here, if we solve it in this case, if you solve it and then if you can implement it, your filter would look something like this. We have all seen that. Okay. Now, when in the case 1, when we are putting a is equal to 0.5 and we are getting or giving an impulse input where xz equals to 1, then 0 0 0 0 like that, and if you see the output y, it is 1, 0.5, 0.25, 0.125. Okay, so I hope all of you will be able to calculate or compute this output. Okay, then coming to the second case where a is equal to 1, but we have we have x equals to 1 0 0 0, which is the input impulse input, and yz it is equals to 1 1 1 1 1. Okay, right? So why this is happening? Because a is equal to 1, input is coming 1, so this input is delayed, again it is getting multiplied with 1, it is going as the output, again that 1 it comes and it gets multiplied with 1, again you are getting that output. Okay, in the first case this a was 0.5, so 1 it was multiplied by 0.5, in the second case it was 0.5, so again we got the 0.5, again it gets multiplied with 0.5, so we get 0.25 as the output, and so on. Similarly, when this a it becomes 1.5, 1 becomes in the next cycle 1.5, then that 1.5 gets multiplied with again 1.5, so then it becomes 2.25, and so on. Okay, so you can see the output in the third case, it is exponentially growing. So at time tending to infinity, small n tending to infinity, we will be having an amplitude that would also be tending to infinity. Okay, so hence in the third case, the filter it is regarded as the unstable filter. So in all the three cases, the wonderful thing is that we have the same architecture. Okay, if you look into the implementation of the filter, it is the same. Only what is changing? Only the value of the multiplier it is changing. Okay. Now coming to the IF filter design. In the IF filter design, we have basically four methods. First one is the impulse invariant method. Second is the bilinear transform method. Third is the frequency transformation method. Okay. And the fourth one is the approximation of derivative methods. Okay. So in this course, we will be discussing about these four methods. Okay. So in the impulse invariant method, what happens is that suppose we are having a pole at 1 by s minus pi, so it would be transformed into 1 by 1 minus e to the power pi capital T into z inverse. Okay, into z inverse. Okay, so where capital T is the sampling period, which is nothing equals to 1 by fs. Okay, and pi, what is it? It is the location of the pole. Okay, because if you put this as 0, s minus pi equals to 0, so we get s equals to pi. Okay, so when we have s equals to pi, so herein it transforms to z equals to e to the power pi t. Okay, so from here we have two equations, s equals to sigma plus j omega 1, which is the conventional one, and the second is z equals to e to the power st. And if we put this s over here, so we get e to the power sigma 1 plus j omega 1 t. So you then find out this real component, e to the power sigma 1 t multiplied by e to the power j omega 1 t. So the modulus of z, it is equals to e to the power sigma 1 t, and phase of z it becomes omega 1 t. So if you see, if sigma is 1, it is less than 0, so what will happen? If it is 0, then modulus is 1, that means it is a unit circle, it is giving you an information about the unit circle. If it is less than omega 1 is less than 0, that means you will be getting a value less than 1, that means you are within the unit circle, and if it is greater than 0, that means you are outside the unit circle. This is what it is saying. So while we have been designing this filter using this impulse invariant method, if you see this transformation matrix or transformation formula, we are able to create a filter which meets all the requirements for the stable filter. Okay, it is meeting all the requirements for the stable filter. That what does this mean? So if whatever filter you will be trying to make by the impulse invariant method, it will be a stable filter. Okay, if your starting analog filter is a stable filter. Okay, so this is what it is saying. So if you start with a stable analog filter and its equation, then this method will always give you stable digital filter. Okay. Now we know z equals to r into e to the power j omega, but we also know that z equals to e to the power st. Okay. So if we equate these two values, so we get r e to the power j omega is equal to e to the power sigma t multiplied by e to the power j omega t. Okay. So r is equal to e to the power sigma t, and our magic equation is omega equals to omega t. Okay. Where omega, which is the analog frequency, it is equal to digital omega by t. In other words, we can say analog frequency is directly proportional to the digital frequency. Okay, but we all know that digital frequency can only occupy values in the range of 0 to 2 pi, and thereafter what happens? Again 0 1 2 3 4 it starts. Okay, so again 0 1 2 3 4 it starts. So what is happening? Multiple analog frequencies are being mapped to a single digital frequency. Multiple analog frequencies, they are being mapped to a single digital frequency. Okay, and hence we have many to one mapping of the frequencies. Okay, so due to this, what we can have? We are having the overlapping of the frequencies. So what is happening? 0 to 2 pi. Suppose you are having a low frequency. Again, when you reach, you are continuing in the digital domain, the high frequencies are being mapped. So low frequency components are getting mixed up with the high frequency components. So what we discussed about this phenomena, it is regarded as the aliasing. Okay, it is regarded as the aliasing. So you have to be very careful about the aliasing while designing filters using the impulse invariant method. Okay, so if you start with a a stable analog filter transfer function, you will always be having a stable digital filter while you are designing with the impulse invariant method. But the problem would be that if you do not take care, you will be having problem associated with aliasing. Okay, so you need to take care of that. Okay, so here we are having some specific transformation equations. So this one we have already discussed. This is the basic transformation equation. 1 by s minus pi, it would be transformed to 1 by 1 minus e to the power pi t z inverse. So this is called the distinct poles. Okay, then you can have 1 by s plus pi to the power m. Then you see we have to use this equation where we can say that we are having multiple poles. But this kind of what you call equations, they can also be converted into the distinct pole equations. How we can convert it? By using the partial fraction. Say a by s minus p0 plus b by s minus pi or p1, we can convert it. So multiple poles can also be represented in distinct poles and then implemented. Otherwise, if you are not able to do that, then you can directly use this equation, this transformation equation, to convert the impulse invariant method into this one. Then there are couple of other methods: s plus a divided by s plus a whole square plus b square. Then you get 1 minus e to the power minus at. multiplied by cos b capital T z inverse, and the denominator it goes something like this. And also you can have the form, you can have the equation in the form of b by s plus a whole square plus b square, and then you will be having the transformation equation over here like this. Okay. One thing you have to keep it in mind while you are solving this equation cos of bt, please keep it in mind that your calculator should be in the radians form. Okay? Then only you will be getting the thing. Because while calculating the what do you call this sine and cos functions, you can use both the degrees and the radians, but we have to keep it in mind the calculator's unit should be in the radians while computing using these complex poles things. Okay, transformation equations. Now let us take uh, some example. So HS equals to 1 by s square plus 5s plus 6. So all pole filters. Okay. So this equation it can be broken down into s plus 2 multiplied by s plus 3. So a divided by a plus s plus 2 plus b divided by s plus 3. So we need to break this equation through the partial fraction, and by doing this, we find that a is equal to 1 and b equals to minus 1. I hope all of you knows how to perform the partial fraction. Okay, so from here we have to go over here. Now if you remember correctly, what was our equation? Our primary equation, it was 1 by s minus pi. So we have to convert this plus into minus form. So that's why if you see we have changed it to 1 by s minus of minus of 2 minus of 1 by s minus of minus 3. Okay, so we have to apply the transformation, and since we are not given with capital T, so we can assume it to be t equals to 1 second. Okay, so h of z is equal to, we have just take this and put it into the transformation equation, 1 minus e to the power minus 2t by z inverse minus of 1 by 1 minus e to the power minus 3t by multiplied by z inverse. Okay, now you need to solve it. Capital T is 1, so this becomes 1. Now you solve these things and you get this h of z. Okay, now after this you need to solve it, and it can be a 2 marks question. So in a 3 marks question I can ask you to implement the realize the filter or implement it. So you need to realize the filter after that if it is given. Okay, and then again we can ask you to find out the amplitude and the phase responses. Amplitude and phase responses, how will you find out? डिस्टेंस मेथड में इसमें करने जाओगे तो इट विल टेक यू एजेस. We discuss it. Z is equals to e to the power j omega. Just need to put that thing and you have to compute that. Okay. So if I here filter me. So next question is similar to this. If you see again this thing. Okay. Third question again, if you see the same thing over here. But interestingly, if you see, we are having a multiplier capital T. Okay, we are having a multiplier capital T. Here capital is given by T equals to 0.2, but here we have put as a capital in the capital T as the multiplier. Okay, so why this is happening? So the previous two examples, this one and two examples, here we are implementing the standard impulse invariant method. Okay, in this case we are implementing modified impulse invariant method. Okay. So why that is so? We will come to that in somewhat a bit later. Okay. So if you see, we are having standard impulse invariance method and modified impulse invariance method. Okay. So what happens over here is that the problem in the first method is that when your sampling frequency is much higher than your maximum frequency, in typical case it is greater than equal to 10 of fs, it will not affect your DC gain. Okay, but so in the second case it is much higher. Okay, so it should not affect our DC gain, but at low frequencies it will affect your DC gain. So let us take the example. So this third example over here, 10 by s square plus 7s plus 10. So this equation. So if you look into this DC gain, so in this DC gain, what is happening? H of 0, it is 0 means we are putting s equals to 0. So 0 plus 0 plus 10. So this 10 gets cut out. So we get 1. So it is the DC gain. So when you perform this partial fraction and when you multiply it with capital T, so what is happening 0.2, and when you are doing all these calculations, if you see your DC gain, it is 0.96. Okay. So over here what you put, we have to put z equals to 1. Okay. So at z equals to 1 we are having the DC gain. Okay. So at z equals to 1 we are having the DC gain. So after putting this multiplier we are getting 0.96. Okay. So this is the DC gain. Otherwise, if we had not multiplied this capital T, so what we would have got? We would have got a gain of 0 or 4.8, which is much higher as compared to the this analog DC gain. Okay, in the analog DC gain, we are having 1, and if we had not applied this T, what we would have got? We would have got a DC gain which is almost a multiplied by 5. So it would have distorted our signal. Distorted means it would have amplified the signals in an unwarranted way. Since we have multiplied with capital T, it has toned down the amplitude which is near to the original DC frequency. Okay, and hence in exam, when if you get any of these examples, so until and unless it is given that you implement the numerical using the standard impulse invariance method, it is understood that you will be implementing it with the modified impulse invariance method. Okay, so if capital T is not given to you, so you can assume it to be 1 second and your life will be becoming easier. Okay, now similarly we have to convert this analog filter with system transfer function hs equal to s plus 0.1 divided by s plus 0.1 whole square plus 9. So this 9, it can be represented as 3 square. So this equation is becoming s plus a divided by s plus a whole square plus b square, right? So if you see, we already have a transformation equation for this. However, in this case, what we have done is that we have implemented this partial fraction method and we have solved this one. So you can just solve it using either of this method. So this while we are doing this partial fraction method over here, It is since we are having these complex numbers in the denominators, it is a bit complex. So this solution has been given over here. So you can look into this how we have calculated a1 equals to half for the a star 1, which is also again half. It should be calculated in the similar way. For a1 it has been given, and for a1 star you should calculate on your own. And once you have done this, see, we are in the form of 1 by s minus pi equation. So you can use that formula and then solve it. Okay. Plus, keep it in mind that these cost functions, whatever you are getting, it should be, while calculating, it should be in radians. Okay. So impulse invariant method, it helps us in converting analog filters to digital by sampling the impulse response of the analog filter. Okay. So, what is the advantage? It is simple to implement, maintains exact correspondence with the analog impulse response at sampling rate, and disadvantage is that aliasing can occur if the analog filter has high frequency components that exceed half the sampling rate. Okay. So, and then applications suitable for low pass filters where aliasing is less problematic. Okay. So impulse invariant method, it is specifically used to design only and only low pass filter. Okay. Is it okay for you? Have you got the point why it is needed? This is needed because higher frequency points, they are getting uh, this problem of multiple mapping. So to avoid that, only the low frequency components, if you see, they are getting mapped in a unitary way. So if you apply an this anti-aliasing filter, then you will only be able to create the low pass frequencies. Okay. Otherwise, if you want to make a high pass frequency thing, it becomes difficult to uh, design using the impulse invariant method. Okay. So when we are having high sampling rate, fs is greater than equal to 10 of f of max, we need to use this multiplier. Okay. So you have seen that t equals to 0.2 seconds. When it was there, at that time we needed to use the multiplier. But when we are having this t equals to 1 second, that means this normalized sampling frequency of 1 hertz, which was much higher. So under those conditions we did not multiply. But typically if you want to do, because you may get confused, so while solving the problem, you should always use the capital T as the multiplier. Okay. And if the T value is not given, you should be using T equals to 1 second. So anyhow, your life will be made easier. And you have to write down that this numerical is being performed by modified impulse invariant method. Okay. So with this, we will stop today. So try to solve this three numerical and see if you find any difficulty. So solve the first one and second one specifically, because as I told you, capital T needs to be incorporated.